One form for the equation of a straight line is y equals mx plus c. C is the y-intercept of the line. We can see that if we set x equal to 0, we get y equals c. So when x is 0, y is c. Now m is the slope of the line. That means if we pick any point on the line, say this point here, increase x by 1, so we move one step to the right, horizontally to the right, then the distance up or down we go is m. Well, for this particular line we can see that m is actually positive, so the slope of this line is positive. If m was negative, we would be going down a certain distance and the line would be going in this direction. Now the angle in here in this triangle is theta, and the tan of theta is opposite over adjacent, m over 1, which is m. So the slope of any line is the tan of the angle that it makes with the positive x-axis. So here theta happens to be an acute angle. Theta is measured anti-clockwise from the positive x-axis, but the same result will hold if our line is like this and theta is an obtuse angle. In this case the tan of theta will actually be negative, so we will indeed get a negative slope, a negative value of m for this line, say. Now suppose we have a second line. It's y equals nx plus d, so all lines have to have this form, an x term and a constant. If m is equal to n, then the slopes of the two lines are the same, which means the two lines will be parallel. Now we are assuming that the slopes are different, so the two lines are not parallel, which means that they will intersect at one point. Now we know that the tan of the angle that a line makes with the positive x-axis is equal to the slope of the line. So the slope of this line is the coefficient of x, which is n, and that must equal the tan of psi, where psi is the angle measured anti-clockwise from the positive x-axis to our line. We are interested in getting the relationship between the slopes of the lines, that is between m and n, when the lines are perpendicular to each other. So we want these two lines to be perpendicular. But we know that the exterior angle of a triangle is the sum of the two interior and opposite angles. So psi is equal to theta plus 90 degrees. So this comes from the fact that the three angles in a triangle add up to 180. So if we add these angles inside the triangle, we get 180, and if we add these two angles, we also get 180. So if we subtract this angle from both sides, we end up showing that psi equals theta plus 90. So we can turn that around to see that the difference between psi and theta must be 90 degrees. Okay, we can turn this around again to get theta in terms of psi. Now we're going to get the connection between n and m, where m is tan theta and n is tan psi. So we're going to take the tan of both sides of this equation. So we have to get the tan of theta, and that's equal to the tan of psi minus 90. So this is true for any two lines. The tan function is the same as the sine over cos of the angle. We can simplify sine of psi minus 90 degrees by using this identity here. We just plug psi in for A and 90 in for B. The cos of 90 is 0, so this goes out. Here we have minus cos psi sine 90. The sine of 90 is 1, so we end up at minus cos psi for the sine of psi minus 90. As for the cos of psi minus 90, we use this identity here. Plug psi in for A, 90 in for B. The cos of 90 is 0, so this term goes out. The sine of 90 is 1. So we get sine 90 by 1, or sine psi by 1, which is sine psi. Since the tan of an angle is sine over cos, cos over sine is 1 over the tan of psi. Now tan psi is the slope of the second line. Tan psi is n. So we see that m equals minus 1 over n. Cross multiplying, we see that the product of the slopes of the two perpendicular lines is minus 1. An easier way to prove that relation actually is to do it geometrically. Let's look at this line here. Pick any point on it. Increase this distance x by 1, say. Then we know that because the slope is m, this distance here is m, and actually it's positive for this particular line. Now imagine rotating this line 90 degrees about the point of intersection. What's going to happen? Well, the horizontal distance is going to become vertical, and the vertical distance is going to become horizontal. So let's suppose that after rotating through 90 degrees, this point ends up here. So this line will end up on top of this line here. Okay, so this horizontal distance of 1 becomes a vertical distance of 1, and the vertical distance of m becomes a horizontal distance. Because if we rotate a horizontal line through 90 degrees, we get a vertical line. Rotating a vertical line through 90 degrees will give us a horizontal line. So this distance here is m. Okay, so we can use this triangle to get the slope of this line. We just put the vertical distance over the horizontal distance. We just put 1 over m. But since we're dealing with a positive line here, where m is greater than 0, and since the slope of this line is negative, we have to stick a minus sign in front of this. So this is the slope of the second line, and of course we know that that's equal to n. And from that we get nm equals minus 1. Here's just a few examples of pairs of lines. We want to see if the first pair of lines are perpendicular. Well, the slope of this line is minus 1, the slope of this line is plus 1. If we multiply the slopes, minus 1 by plus 1 gives us minus 1. So this pair of lines is perpendicular. What about this pair of lines here? Well, what's the slope of this line? We have to get into standard form, in the form y equals mx plus c. So we bring the x term over, and we get y equals minus x plus 1. So the slope of this line is, the coefficient of x is minus 1. The slope of this line here is also minus 1. If you bring the x term over, minus 1 by minus 1 is plus 1. So these are not perpendicular. In this example here, the slope is 8 divided by 2. We have to divide across by 2. It's in the standard form now, so the slope is 8 over 2, which is 4. What about the slope of this line here? Well, the coefficient of x gives us the slope. It's minus a quarter. If we multiply 4 by minus a quarter, we get minus 1. So this pair of lines is indeed perpendicular. Next, we will consider the idea of a normal line to a curve. Here we have the curve y equals x squared, and we're looking at the point 1, 1 on the curve. The tangent line is shown here. It goes through the point 1, 1. It's tangent to the curve at 1, 1. And the normal line is perpendicular to the tangent at the point 1, 1. Now, we know that the derivative of the function at x equals 1, or x naught equals 1, that's what this is called here actually, is the slope of the curve at 1, or the slope of the tangent to the curve at 1. So here's the derivative at x naught. X naught is 1 here, and the slope of the tangent line is the tan of the angle that the tangent line makes with the positive x-axis. In this case, theta is an acute angle. Theta is approximately 63.4 degrees in this case. Now the derivative of this function is actually 2x, and if we work out the derivative at x naught equals 1, that's going to be 2 times 1, which is 2. So tan theta equals 2, and if you get theta, you get approximately 63.4. Now here's the general picture. So we have a general function of x, and here's the tangent line to the curve at x naught, and here's the angle theta. The line makes it the positive x-axis, so the derivative of the function at x naught is tan of theta. That's the slope of the line. Now suppose we want to get the equation of the tangent line to a general curve at a particular point x naught, y naught. So here is the general equation of any straight line, and to determine this line we need the slope of the line and the constant c. Well, the slope of the tangent line is the same as the slope of the curve at the point x naught, y naught. So the tangent line goes through the point x naught, y naught, and the slope of the curve is the derivative of the curve at the point x naught, at the value, the x value of the point, which is x naught. So that's m, the slope of the line. Now what about the constant? Well, we know that the point x naught, y naught is on the line, so it must satisfy the equation of the line. We also know that the y value of the point of contact of the tangent is on the curve, so we have a relationship between x naught and y naught by plugging into the equation of the curve. So anyway, we could use these formulas to get the equation of a tangent line to any curve at a point x naught, y naught. So here is how we get the slope, and to get c we use this formula here. It just comes from the fact that y naught is f of x naught, and we have m. Now in practice we would probably just differentiate the curve, plug in x0 to get the slope of the tangent, and then we just use this formula here for the equation of a line. So in this example we want the equation of the tangent line to the curve y equals x squared at the point 1, 1. That's what we saw in the picture. So we'll probably use method 2. We don't have to memorize a formula. We just get the derivative of the function at x equals 1, and we saw that already. The derivative is 2x, and 2 times 1 is 2. So the slope of the line is 2. So we just use this formula here for the equation of a line. So x naught, y naught is a particular point on the line. It's 1, 1 in this case. In this example, we want to find the slope of the tangent line to the curve y equals sine 3x at the point x equals pi over 4. So we need to differentiate this function. So we differentiate sine 3x. Well, the derivative of the sine function is cos, and by the chain rule we differentiate the angle to get 3. So we multiply 3 by cos 3x. Then we work out the derivative at pi over 4, so we just plug in pi over 4. So we get the slope of the line, which is negative. As you can see, the line is sloping down. It's got negative slope. From that we can get the equation of the line. We have the slope of the line, and we can get the point of contact of the tangent line. Because we know that at x equals pi over 4, we have the point of contact, and we can plug pi over 4 into this to get the y value of it. So we'll have the point of contact and we'll have the slope, so we can get the equation of the line. To find out where this line intersects the x-axis, well, we just set y equal to 0, because all points on the x-axis have y value 0. So we set y equal to 0 and solve for x to find a point on the x-axis that satisfies this equation. Next we will get the equation of a normal line to a curve. So we go back to the previous example. This time we're going to get the normal line at x equals pi over 4. Well, that's easy. We have the slope of the tangent at pi over 4. We found that to be minus 3 over root 2. So the slope of the normal line is going to be got by inverting this and changing the sign. So we just take the reciprocal and change the sign. We get root 2 over 3. That's because if we multiply any number by its negative reciprocal, we get minus 1. And the slopes must multiply to give minus 1 if the lines are to be perpendicular. Now, to find the equation of the normal line, we use the fact that the normal line must have an equation of this form: y equals mx plus c, where m is the slope of it that we've just got. So what we don't know is the constant. Well, we just use the fact that we have the point of contact. The normal line must pass through the curve at the point x equals pi over 4. So we just plug pi over 4 into the equation of the curve to get the y value, and then we plug in here. So when x is pi over 4, we have the y value from the equation of the curve. So if we plug pi over 4 in, we get sine 3 pi over 4. So that's what y is. So the point of coordinates pi over 4 comma 3 pi over 4 must satisfy this equation. Okay, so y is sine 3 pi over 4, but that's actually the same as the sine of pi over 4, which is 1 over root 2. So now we found the constant. So we have the slope of the line and the constant, so we have the equation of the line. So here's a picture of the line that's normal to the curve at this point. Let's take this example here. Find the value of a if the two curves y equals e to the minus 1x and y equals e to the ax are to intersect at right angles. Now, what does it mean for two curves to intersect at right angles? Well, it means that at the point of intersection of the two curves, the tangents to both curves at that point must be perpendicular to each other. So this is the picture that we're after. Y equals e to the power minus x is a decreasing function of x. As a matter of fact, as x tends towards plus infinity, e to the minus x will tend to 0. So we're after the other exponential function, e to the power of ax. Well, you can see the answer is 1 here, but we're looking for a. Okay, so we don't know the answer, so we need to consider the point of intersection of the curve e to the minus x and e to the ax. So we put them equal to each other, because the y value of the point will be the same, and both of these are equal to y, so we put them equal to each other. And the base numbers e are the same, so the powers must be the same. So we have to see what a must be for these two to have a point of intersection. Well, if a equals minus 1, these two curves will obviously have a point of intersection, but then they're the same curve, so we don't want that. We just get e to the minus x equals e to the minus x, and that's true for all values of x. So we have to consider the situation where a is not minus 1. Well, if a is not minus 1, the only way that this identity can be true is if x is equal to 0. Then it doesn't matter what a is, this identity will be true. So remember now that x equals 0 is the point of intersection of e to the minus x and e to the power of ax, no matter what a is. But we have a constraint on a. A can't just be any old value, because we want the curves to intersect at right angles at x equals 0. So we will be interested in the slopes of the tangent lines to both curves at x equals 0. So let's get the slope of the tangent line to the curve y equals e to the ax. To do that, we need to differentiate it. So we just use the chain rule. If we differentiate e to the power of something, we get e to something back, then multiply by the derivative of the power. So that gives us a, since a is a constant. So that's the slope of any tangent to the curve y equals e to the ax, and at x equals 0, the slope is ae to the power of 0, which is a. Now we get the slope of the tangent line to the other curve at the point of intersection of the two curves. So we differentiate this. So use the chain rule here. We get e to the minus x back, differentiate minus x, get minus 1. Plug in x equals 0, because that's the x value, the point of intersection. That gives us minus 1. So now we have the slopes of the two tangent lines. They are a and minus 1. And we want the tangent lines to be perpendicular to each other. That means the product of the slopes must be minus 1. And that in turn leads us to a equal to 1. So for the other curve, a must equal 1. So the equation of the other curve is y equals e to the power of 1x. You can see that this is an increasing function of x, and they intersect at a point with x value 0. The y value would actually be e to the 0, which is 1. So this point has coordinates 0, 1.